Hi, I'm Daze Thomas, Assistant Professor, Department of Artificial Intelligence and Data Science from SNS College of Engineering. Last class we discussed about deadlocks. So today's class we'll discuss about methods for handling deadlocks. We have to ensure that the system will never enter into a deadlock state. For that we have two methods. One is deadlock prevention, another one is deadlock avoidance. Deadlock prevention allows the system to enter a deadlock state and then recover. It ignores the problem and pretend that deadlocks never occur in the system used by most operating systems, including Unix. So we'll see deadlock prevention in detail. Restrain the ways a request can be made. There are different deadlock categorizations we saw. One is mutual exclusion, hold and wait, no preemption, and circular wait. So we'll see deadlock prevention in each situation. Okay, in mutual exclusion, we can prevent deadlock by non-shareable resources, not required for shareable resources. So if it is not shareable resources, it will be only in read-only files. That is an example. Must hold for non-shareable resources. Okay, and next one is hold and wait. Must guarantee that whenever a process requests a resource, it does not hold any other resources. It requires process to request and be allocated all its resources before it begins execution, or allow process to request resources only when the process has none allocated to it. So in these two situations only a process can request for a resource. This results in low resource utilization and starvation is also possible. In no preemption, if a process that is holding some resources requests another resource that cannot be immediately allocated to it, then all resources currently being held are released. Preempted resources are added to the list of resources for which the process is waiting. Process will be restarted only when it can regain its old resources as well as the new ones that it is requesting. And in the case of circular wait, impose a total ordering of all resource types and require that each process requests resources in an increasing order of enumeration. This is an example for deadlock. And this is an example for deadlock with lock ordering. Next one is deadlock avoidance. Requires that the system has some additional a priori information available. Simplest, this is the most simplest and useful model that each process declare the maximum number of resources of each type that it may need. The deadlock avoidance algorithm dynamically examines the resource allocation state to ensure that there never be a circular wait condition. Resource allocation state is defined by the number of available and allocated resources and the maximum demands of the processes. Next one is save state. When a process requests an available resource, system must decide if immediate allocation leaves the system in a safe state or not. If a system is in safe state, if there exists a sequence of processes P1, P1, P2, etc. up to Pn of all the processes in the systems, is that for each Pi, the resource that Pi can still request can be satisfied by currently available resources plus resources held by all Pj with j less than 1. That is, if a process P1 P1 resource needs are not immediately available, then Pi can wait until all Pj have finished. When Pj is finished, Pi can obtain needed resources, execute, return allocated resources, and then terminate. When Pi terminates, Pi plus 1 can obtain its needed resources, and so on. These are some basic facts. If a system is in safe state, that implies that there is no deadlocks. If a system is in unsafe state, there are possibility of a deadlock. The avoidance implies ensure that a system will never enter an unsafe state. So this is the diagram where you can see safe state, unsafe state, and inside unsafe state you can see a deadlock. So if a system is unsafe, there are chances for deadlock. If a system is in safe state, there are no chances for deadlock. That's all for today's class. Thank you.